So good morning, everyone. Today the session will be on pollutants. And we will start with Nox formation. Now, there are several mechanisms which are responsible for the formation of Nox. The first one is that proposed by Zeldovich in 1946. It's called also thermal NO. The reason why they call it thermal NO is because this reaction mostly takes place at high temperature. This starts with the attack from O atoms on molecular nitrogen to produce NO and a nitrogen atom. This nitrogen atom can be oxidized by reaction with O2 to produce NO and form also O atoms that can be recirculated in the first reaction. And finally, nitrogen atoms can react with hydroxy radical to produce NO and NH atom. The global rate of NO formation can be written this way. And you can see that the global activation energy is very high. This is the reason why this process is only effective at high temperature. The second mechanism is called prompt NO, proposed by Fenimore in 1979. This is the interaction between molecular nitrogen and the hydrocarbon radicals. So CH reacts with N2 and producing NCN plus H. In the old days, they were writing HCN plus N, but in fact, this reaction is spin forbidden. So this goes to NCN. There is also a reaction of CH2 radicals with N2, which produces HCN plus NH, and finally C plus N2 giving CN plus N. So these three key reactions are followed by another set of reactions of the products. HCN, which react with a radical or an atom to produce CN, NCN, which can be oxidized by O atom to produce NO and CN, NCN reacting with OH radicals, producing HCN plus NO, NCN reacting with H atoms to produce HCN plus N, and finally two reactions of NCN with O2, one giving NO plus NCO, and the other one giving NO and CNO. So this reaction is important at lower temperature. And in fact, when you are able to remove the thermal NO, the remaining information of the NO goes through this reaction mechanism here. The third mechanism was proposed in 1974. It goes through the formation of N2O. So N2 plus O gives N2O, and N2O can react with H atom to produce, to reform N2 plus OH. But N2O can react with O atoms and produce 2 NO, or produce N2 plus O2. N2O can react also with OH to produce N2 plus HO2, or HNO plus NO. This reaction is mostly important at high pressure, because you see it's a three-body reaction, so higher pressure favor this reaction. And also, it's more important in fuel-lean condition when there is an excess of oxygen. The fourth set of reaction is the Nnh mechanism proposed by Bozzelli and Dean in 1995. There, N2 is attacked by H atoms to produce NNH, and NNH can be either reduced to form N2 again, or can be oxidized to produce N2O, to produce NH plus NO. NNH can be oxidized by OH, forming N2 plus H2O. It can react with molecular oxygen to form N2 plus HO2 or N2 plus H plus O2. And there is also possibility to have a reaction between NNH and NH to form N2 plus NH2, and NNH plus NH2 to form N2 plus NH3. And finally, NNH can react with NO to form N2 plus HNO. What is missing here are the reaction of HNO. HNO usually decomposes to form H plus NO. This reaction mechanism is usually less important than the others. And now this is a peculiar mechanism for fuels which contain nitrogen. It can be the case for coal, for example, or heavy fuels. And then there are two channels from the fuel nitrogen. It can produce intermediately HCN or ammonia, and both will produce NH2. And this guy can react with NO to form nitrogen. This is a reduction reaction. Or it can be oxidized and produce NO. This reaction mechanism can occur at relatively low temperature compared to the Zeldovich mechanism. So the kind of structure that you can find in this type of fuels are presented here. So aromatic rings with a nitrogen atom here, aromatic rings connected by a carbon chain, and these two nitrogen here. That there can be also an aromatic ring with some substituent like OH, COH, and these other structure with OH and also the carboxylic acid here, or two carboxylic acid functions. We can find also nitrogen in these saturated or partially saturated structure, such as this one, carbazole structure, and all these other structures. And finally, amines, sorry, amines like urea or all these other structures. So once you get from coal, you get tar nitrogen, and tar nitrogen will produce HCN, and then you have the mechanism of oxidation of HCN here. HCN is oxidized by reactions with O atoms to produce NH or NCO, or it can produce CN by oxidation of OH, followed by reaction with molecular oxygen to form also NCO. And NCO can react with HCN to produce HNCO. HNCO can be oxidized and form NCO. They can also react with H atoms to produce NH. And by oxidation of NH, you get NO here. You also get NO through the oxidation of NH2 by oxygen atom forming first HNO, which will either decompose or react with radicals of atom to produce NO. There is a formation of N2O also, which occurs through a range of reactions. One of them is the reaction of NO with NCO or NH, producing N2O. N2O is a problem. It's a global warming species, and it has long life in the troposphere. It can sit there for about 40 years. So it's a very important species. And it's well known that coal combustion produces N2. N2O can be destroyed in combustion if it's at high temperature, really high temperature, which is not always the case. So there has been several attempts to reduce the emissions of NO. So there are different approaches. Either you try not to produce NO, or you produce NO and you try to make it react with another species to reduce it and form molecular nitrogen. So the first option would be the optimization of a burner parameter. This is the case for low NOx burners. So burner parameter optimization techniques and low NOx burners are used to limit NO production during combustion. These burners are specially designed to control the mixing of air and fuel to create more or less turbulent flames stabilized by internal recirculation zone. The temperature of the flame can be lowered, and thus limiting the production of thermal NO. This type of burner works as a dual internal staging of fuel and combustion air. The fuel burns with primary air under fuel-rich condition, and secondary air is injected over the main combustion zone and completes the oxidation of the fuel. This increases the volume of the flame, which decreases the flame temperature, and thus reduce the importance of thermal NO. Show you a scheme of this type of burner. So you have here the recirculation zone, primary zone, which is fuel-rich, excess of fuel compared to air, and the injection of secondary air here that will burn the unburned species. So this way you can reduce significantly NOx emissions. We can use flue gas recirculation. It's similar to EGR used in piston engines. So the recirculations of fumes inside the oven or burner allows a dilution of the flame, and again by dilution you decrease the temperature. This way you can use 20 to 30% of flue gas recirculation. This stoichiometry is not modified since the concentration of oxygen in the fumes is negligible, and the efficiency is relatively low, around 20%, because the contribution of thermal NO doesn't dominate in installation burning coal. Fuel staging of the fuel allows alternation between fuel-rich zone and fuel-lean zone, which limits the temperature of the flame, improve the distribution of oxygen, and limits Nox formation. And then these are post-treatment. Chemical reduction of Nox. So the first one is the selective non-catalytic reduction, SNCR, proposed by Lyon in 1974. So on these plots, we show the effect of NO initial concentration on its removal by ammonia in fuel lean conditions, very lean conditions. The initial concentration here were 1000 ppm of ammonia, residence time of 100 milliseconds, and we used 500 ppm of NO for the open symbols, those, and 1000 ppm of NO, the closed symbol, the black symbols. And the data were compared to simulations. What we can see is that when we plot NO divided by initial concentration of NO, you can see that there is a sharp drop here, and you reach a maximum conversion of NO around 1250 K, and then the concentration of NO goes up again. This is another example. This is the same kind of plot, but for ammonia, and you can see that in both cases we consume fully ammonia. And there is a side reaction, unfortunately, that produces N2O. And you can see that N2O is accumulating before it decreases. And the maximum is above 1300 Kelvin, between 1300 and 1400 Kelvin. So we can optimize the reduction of NO if we stay below 1250. Then we have less formation of N2O and high reduction of NO. These are other examples of the reduction of ammonia by the reduction of NO by ammonia, sorry, where we also see the formation of N2O. So here we operate with different initial concentration of NO and ammonia. So we have 500 ppm of NO initially, and we introduce the 500 ppm of ammonia, and these are the data here, and then 1000 ppm of ammonia, and this is the solid line. So you can see that if more ammonia you introduce in the system, more reduction of NO you get. And this is another example of working with a different reactor. These were performed in Denmark in 1995, and by introducing ammonia, you see this sharp drop here, and it's about at the same temperature between 1200 and 1300. What is interesting is that ammonia and NO interact, and when you when you oxidize ammonia. So we have two sets of experiments here. They were performed in a jet stirred reactor at 1 atmosphere. We have 1000 ppm of ammonia in fuel lean condition. So in the case of the open symbol, we don't introduce NaNO. So we get a conversion of ammonia, which starts around 1300 Kelvin. And you form here H2O, H2O, yeah. And then if you introduce 500 ppm of NO in the system, what you can see is that the reaction of oxidation of ammonia starts much earlier. Here we are at 1200, we are at 1300, so it's 100 Kelvin less. So NO has a strong effect on the rate of consumption of ammonia. And this kind of result, I don't think, was observed before we did the experiments. Maybe it was observed, but not reported. We tested against our data several literature mechanisms, and we've been surprised to see that the one that we published in Progress Energy and Combustion Science for Hcn oxidation was working pretty well compared to the other mechanism in the literature, which all predict too fast oxidation of ammonia. And so we run some kinetic analysis in order to figure out what were the reactions responsible of this acceleration of the conversion of ammonia by NO. The computation show that it occurs via several reaction pathways leading to OH production, which is the main species involved in ammonia oxidation. So under these conditions, we have this reaction of NNH plus O2, which gives N2 plus H2O, and H plus O2 plus M, which gives H2O. Production of OH results from a sequence of reaction involving NH2 plus NO, giving NNH plus OH. And then NNH can decompose, produce H atom, which reacts with O2 to produce OH. And finally, NO also reacts with HO2. It's a fast reaction, producing N2O and O2. This reaction is also very important in the troposphere. It is responsible for the formation of NO2. The presence of NO2 is clear when you look at the sky and you have a brownish color. Well, this is N2O. And we also considered the data on the burning velocity taken from the literature. And our mechanism represent reasonably well the data. It's on the upper side. The kinetics of the reaction NH2 plus H giving NH plus H2 and HNO plus H giving NO plus H2 were updated in order to improve the modeling here. When you are burning real fuel, it's frequent that you have both NOx and SOx in presence. And therefore, we've been looking at the possible interaction between Nox chemistry and sulfur chemistry. So this is here an example on the effect of SO2 on NO removal by ammonia on the fuel lean conditions. The conditions are given here. So again, we work with relatively small concentration of ammonia and NO, and relatively high concentration of SO2. And what we can see is that SO2 has no effect in terms of degree of conversion of NO, but you will have a shift towards higher temperatures when you introduce SO2. So SO2 will slow down the process at a lower temperature, but will not significantly change the overall conversion of NO and consumption of ammonia. It has a slight effect on the formation of N2O, as can be seen here. Tends to limit the formation of N2O. We performed several experiments of this type, and in every conditions we investigated, we have the same behavior. We have a shift towards slightly higher temperature of the different profiles. And this is an example. So this one was still at fuel lean, and here it's in fuel rich. So excess of fuel compared to the amount of oxygen. And when we introduce SO2, you see that the reactivity is shifted towards higher temperatures. It's also here for formation of N2O. We try to understand how it works. We know that the reduction of NO goes through the interaction between NO and NH2. So NH2 is produced by the reaction of NH3 with OH. It's the major route. There is another one, minor route, by reaction with oxygen atom, producing NH2 and OH. NH2 reacts with NO through two channels. One giving directly molecular nitrogen, and the other one producing NH, which will decompose and produce N2 plus H. OH radicals are produced through several reactions. The main one is the reaction of NH2 with NO, producing NH plus OH. And under this condition, the main branching reaction is a bit less important. There is also the reaction I mentioned before, NO plus HO2, giving OH, and finally NH3 plus O giving OH. O atoms are produced by this reaction exclusively, the main branching reaction of the system. SO2 contributes moderately to the removal of O atoms to form SO3. And the model indicates that SO2 reacts mostly through three reactions. The main one being SO2 plus NH2 giving NH2SO2, and the others being SO2 plus O giving SO3, and SO2 plus H giving HOSO. HOSO formed here recycles SO2 in this reaction. So as soon as it is produced, it reacts with O2 and reform SO2. What is interesting is that the sequence of reaction 13 and 57, if you add those, so you have HOSO plus O2 giving HO2 plus SO2 and H plus SO2 plus N giving HOSO plus N. So you can cancel what is in the reactant side, and it appears also in the product side. So you remove HOSO, you remove SO2, you can remove N if you want, but it doesn't matter. So if we don't, we have H plus O2 plus M giving HO2 plus N. And if you remember, I told you that this reaction is responsible for the decrease of the oxidation of hydrogen that we saw 2 days ago. So it results in a reduction of the radical pool, since the fraction of H atom will not reacting in this fraction will not produce OH by reaction with O2, and O2 and OH via reaction 100 NO2 plus H giving NO plus OH. So under such condition, introducing 1000 ppm of SO2 reduces the rate of production of O atoms by a factor of almost 2, and that of OH by a factor also of almost 2. And because O and OH are the major oxidation agents for ammonia, the rate of ammonia oxidation is reduced by also a factor of almost of 2, resulting in the reduction of the rate of NH2 production by a factor of about 2 again, and in a reduction of 42% of NO consumption rate. We studied also the effect of SO2 on the oxidation of different systems. The first, the first system that we considered was COH2, syngas mixture, and we plot here the mole fraction of CO as a function of temperature. And if we oxidize this mixture without SO2, you see that at around 950 K, all the fuel is gone. But when we introduce 1.2% of SO2 in the system, there is a strong effect here, a shift by, well, more than 200 degrees almost. And we have the same behavior here under different conditions where we introduce only 0.3% of SO2, but there is a clear shift in reactivity. And kinetic modeling showed that this inhibition is due to H plus SO2 giving HOSO, followed by HOSO plus H giving H2 plus SO2. So in this process, you are consuming 2 H atoms, first one here, and then second one here to reform H2. So this explains why the overall reaction is slowed down. Another possibility to reduce NO is through the so-called Nox Returning. So there you have this furnace where you have a primary combustion zone here, where you burn the fuel in near stoichiometric conditions, and you produce NO, at least through the thermodynamic mechanism. And then you make a we call reburning zone, where you introduce fuel again. So then you have excess of fuel compared to oxygen, and you will have the possibility to get interaction of hydrocarbon radicals with NO and produce N2 and some intermediates, which contains both hydrogen, carbon, nitrogen, and oxygen. You cannot release these species in the atmosphere, so you then introduce air again to burn out these species. And then these species which were produced intermediately, they will be oxidized and produce NO. So you cannot fully remove NO with this system, because intermediately there are species which are not, which are different from N2, and those will be oxidized and reform NO. So I will show you some example of laboratory results where we oxidized a fuel. So here we used a mixture of methane and ethane, 10% of ethane compared to methane, in order to mimic a simple natural gas. So we did several types of experiments. We did experiments where we keep the temperature constant, and we vary the equivalence ratio, and we plot NO, Hcn, and total fixed nitrogen. So we have here the variation of NO, the squares. And you can see that above about 1.6 equivalence ratio, then you are less efficient reducing NO. And while you are removing NO, you are producing intermediates. Among them, the most important is HCN. And you see that you have an accumulation of HCN. So when we were reducing NO by ammonia, we had intermediately N2O form. Here it's HCN, which is formed. So and here this TFN is the results, the overall result of the reduction, and so it tells you that reduction can go up to 50% because there is this HCN, which in turn in real life will be converted in NO again. If we operate at higher temperatures still, you can see that the conversion is a bit better, but it is still maximum around, well, just above stoichiometric conditions, between 1 and 1.25, similar as here. And finally, if we look at the same system at much lower temperature, 1250 K, you can see that there is not much of, there is 30% conversion only. And of course, the formation of HCN is much less. So it's interesting to note that we can optimize the reduction of NO in a range of equivalence ratio which is not very high, because if we go back to this system, it means that we don't need to introduce a lot of reburning fuel, which means that it's not so expensive to operate. If we were needing phi equal 2, then it would mean introducing lots of fuel, and it would be more costly. So this is not the case. Here we looked at the impact of temperature, and so we plot NO as a function of temperature and the formation of I'm sorry, these are here. These are the methane, CO, and CO2. So methane, CO, and CO2, and here and here it's A. So it's also it's also methane, CO, and CO2. We looked at the reaction pathways which are important in this system, and we did experiments with a range of fuels. So I showed you results with methane plus ethane, but we did it. We ran some experiments with several pure fuels, single fuel, like ethylene, acetylene, propylene, butane, isobutane, butylene, and so we ran the experiments. We simulated them with a detailed kinetic reaction mechanism and used it to interpret the results. So when ethylene is the fuel, it looks a bit busy and complicated, but so I will tell you how it's organized. So here on the right hand side, you have the chemistry of the fuel, and here the chemistry between fuel radicals and NO. Okay, so we start with ethylene. Ethylene is oxidized by a reaction with OH and O. It can also react with H atom abstraction by a reaction with H, producing vinyl radicals, which can produce acetylene by decomposition. And by oxidation, you get formaldehyde and HCO. The other channel is the oxidation of ethylene by O atoms, producing this binoxy species, which can decompose and produce ketene, CH2 double bond CO. And this species can react with H atom to produce CH3 and CO. And then you are going back to formaldehyde chemistry. And it can also react through H atom abstraction to form ketenyl, HCCO here. And HCCO can also be produced by the oxidation of acetylene reacting with O atoms. And then you get this HCCO. HCCO is really a key compound. It reacts with NO to produce HCNO. And HCNO can partly reform NO by oxidation by O atoms and OH radicals. So you get NO, and then you have a kind of interplay between NO and HNO. So NO can produce HNO, but HNO mostly reform NO. So this is not the interesting part. The interesting part is here. Once you have HCNO, it can react with H atom and produce another key species, HCl, that we saw on the plots before. And HCl can react through different pathways, which produce CN, NCO, and NH. and NCO can produce HNCO, which itself can produce NH2. NH2 can react with NO. We saw that with ammonia already, and it gives N2 here. And NH produced from NCO or from HCN can react with NO to form N2O, but also to form N2. So these are the main pathways that we could figure out when we were dealing with this chemistry. And we have something very similar if we start with acetylene here. So we can say that we are one step further, and we are getting closer to the formation of HCCO. So from acetylene, the main pathway is the oxidation bioatoms to produce HCCO, and then it's exactly the same scheme here. It goes through the intermediate formation of HCNO, HCN, and then the same chemistry goes on, and finally you can get N2. So it's not so complicated. If we start, so now we go back to a reactant which is further from HCCO. If we consider normal butane, will be oxidized and produce different radical. Primary C4H9, secondary C4H9. It can, by H atom abstraction, it can also decompose and produce C3 and C2 alkyl radicals. Those will oxidize and produce ethylene, and then we are back to the previous system where ethylene was the fuel. So the oxidation of ethylene goes to CH2, HCO, CH2CO, HCCO. Okay, and all this chemistry is associated with the intermediate formation of propylene. We have all the C3 branched, and some of these reactions will finally produce acetylene here. So chemistry is very similar, and once we've studied all these reactions, all these systems, we can summarize by saying that C1 to C4 hydrocarbons will produce some intermediates like ethylene, which is most likely the main intermediate of importance. The vinyl radical, and you can have also in some conditions, especially when you have a C4 fuel, you will get propylene. The oxidation of propylene will give ethylene as an intermediate, and ethylene gives C2H3 vinyl radicals, which will produce acetylene. And acetylene by oxidation with O atoms produces HCCO. HCCO reacts with NO, mostly giving HCNO. Unfortunately, HCNO is mostly oxidized and gives back NO. But there is a fraction of HCNO which react with H atom producing HCN as an intermediate. And then you are dealing with HCN chemistry. And this is what is described here by the formation of CN, NCO that can react with H2 to form HNCO, then produce NH2, which react with NO to produce molecular nitrogen. And NH can react, well, it's the same reaction, it's the duplication, but then here it starts from it. So you see that things are relatively simple, and NH here reacts with NO and produces N2. And you can have interaction of N2O with H atoms, especially H atoms, which can form N2 also. So we investigated many fuels, and what we can see is that for most of them, the optimum is between phi equal 1. Sorry, I'm not between phi equal 1 and phi equal 1.2. But concerning the temperature at which you get high NO conversion, it can differ very much, and you must notice here that acetylene is extremely efficient to reduce NO. Why that? Because acetylene will produce very readily HCCO, which is the key intermediate in this system. And the others are a bit similar, but if we look in more details, we can see that ethylene and ethane, which are here, are also very efficient because they are not far from acetylene. You have just few steps to transform these guys into acetylene and form HCCO. And if we look at the formation of HCCO through the oxidation of different fuel, this is only computations. You can see that in the case of a natural gas surrogate, the mole fraction of HCCO peaks around 1200 K, and below it's a sharp increase. But in the case of the C2 fuels, the formation of HCCO occurs at much lower temperature. That can be seen here with ethane compared to the natural gas surrogate. And finally, we looked at the impact of SO2 on NO reburning. And what we can see is that the residual of NO increases in the presence of sulfur oxide. So this is what we observed here. For two fuels, natural gas blend and even acetylene. So if there were no impact, it would be on this line here. So there is an impact which varies with equivalence ratio. And I will stop here. I have two questions. I will answer these questions. If NO decomposes in presence of hydrocarbons at lower temperatures than the Nnh mechanism, which reactions will be important? Well, it doesn't decompose; it reacts with radicals. Certainly at lower temperatures than the Nnh mechanism. So the reactions which are important, I showed you, it's HCCO plus NO, but also CH2 plus NO and CH plus NO. As it was mentioned that N2O root three-body mechanism occurs at elevated pressure. So could you explain how the NO formation rate depends on the pressure and activation energy? Well, you have N2 plus O plus M. So since it's a three-body reaction, it's very pressure dependent. And the rate will increase dramatically with the increase of pressure because with increasing pressure, you increase the molecular concentration of the different reactants. So it has nothing to do with the activation energy. It has to do with concentrations. All right, so we can have a break now for 5 to 10 minutes, and then we get back. All right, so we're back. So now we will have a look at another type of pollution, which are unburned hydrocarbons and soot. In the troposphere, there are lots of organics which are present, and this table gives you an idea of what is present there. So by far the first hydrocarbon which is present in the atmosphere is methane, for several reasons. Because of the production of natural gas, or you have some methane that goes to the atmosphere, that escapes and goes to the atmosphere. The other source is a microbial process, and especially in swamp, and also people are growing rice, or cows also emit lots of methane. Is another important hydrocarbon present in the atmosphere, emitted by the alcohols. Same for other saturated hydrocarbons. Ethylene is a chemical which is emitted also by microbial processes. Propylene is emitted by motor engines. Isoprene is naturally emitted by vegetation, and its oxidation will produce some particulates in the atmosphere. So acetylene is emitted mostly by motor engines. Benzene, toluene, it's the same. The alcohols, formaldehyde, acetaldehyde, it's about the same. Acrolein can be produced by biomass burning. Acetone is widely used as a solvent, so it's one source of acids. Can also be produced by combustion. And methanol, it can be also produced by industry, where it's used as a solvent. There may be other sources. And you can see that for most of these species, their destruction, their natural destruction, proceeds through reaction with OH radicals. For unsaturated hydrocarbons, the reaction with ozone is also important. So ozone will add on top of the double bond, form an ozonide, which will decompose and produce two oxygenated products. And regarding acids, they can be removed from air by rain. the use of new types of fuels for ground transportation will be responsible for also the emission of new species. And it's very simple to understand when you are refueling your car. There is not always capture aspiration to capture vapors of gasoline or of diesel, and this goes into the atmosphere. So this is a major source of emissions. Once these species are emitted in the troposphere, they get oxidized. They get oxidized by OH radicals, which will produce another radical from this species. So, for example, if it was methane, you would get methyl radical, which can react with molecular oxygen to form CH3O2, for example. And this peroxy radical can react with NO. NO then is transformed into NO2, and the RO2 is transformed into RO. And NO2 absorbs light. It is photolyzed by solar light and produces NO plus an oxygen atom, and this oxygen atom reacts with molecular oxygen present in air and forms ozone. This alkoxy radical here can react through decomposition or isomerization or reaction with O2 to produce carbonyl products. If they react with O2, they will produce HO2, and the HO2 will interact with NO. We've seen this reaction just recently. So NO plus HO2 gives NO2 plus OH. And NO2 is photolyzed by sunlight, produce an oxygen atom, which reacts with oxygen to produce. And this ozone here is responsible for the oxidation in the atmosphere. As we saw on this table, it will react with unsaturated species and oxidize them. So in the atmosphere, besides isoprene, there are lots of other chemicals which are emitted by the vegetation, especially terpenes. Terpenes are interesting. I already mentioned that. They are interesting because they are part of the natural air pollution, but they have been also proposed to be used as fuel. And so recently we looked at the oxidation of these terpenes, and we could figure out that their oxidation proceeds through multiple pathways, but one of them is peroxidation, isomerization by internal H atom transfer, followed by second addition of O2, isomerization again, and it can be also it can decompose, produce OH radical and a ketohydroperoxide. But the reaction can proceed further, and we can add, well, here we observe the formation of up to 5 O2 molecule on the fuel radicals. And we could observe the different intermediate. And also, I told you the introduction, we could also figure out that we had several HO2 groups in these species by doing HD exchange using D2O. So beside the classical reaction mechanism, peroxidation mechanism, there are additional pathways that are responsible for the formation of highly oxygenated species as those. And this chemistry that we could observe under cool flame conditions are those which are considered in tropospheric chemistry to explain the formation of particulates and secondary secondary organic aerosols. So we observe these highly oxygenated species. This is a mass spec obtained on our sample of limonene oxidation below 600 Kelvin. And you can see all these mass peaks here. But if you look more carefully between 200 and 600, you see that there are still species which are formed, which are very heavy, and they correspond to highly oxygenated species. And we can use this representation, this Kendrick mass defect. If we plot these results using this graph, and here we have so we have on this axis we have the Kendrick mass using the CH2 as a structural unit, and here we have the Kendrick mass defect, which is the difference between the nominal mass and the Kendrick mass. And here it's the equivalent double unsaturation, and we can see that there are some distribution of the molecular formula that we observe, and so we compared our results to literature, especially results coming from smoke chambers, and what we could see is that with smoke chambers, you observe species here that we couldn't see, and these species are very, very heavy. And the interpretation is that since they are operating over several hours, then the processes can go much further than what we can observe under our conditions. But you can see that the rest here is the red dots corresponds to common products form under smoke chamber conditions and in jet stud reactor operating below 600 Kelvin. And the red dots here are chemicals that we observe and which were not reported in these studies, because we operate at very short residence time compared to theirs. We operate at a few seconds residence time, whereas they operate with over several hours here. So again, there is a strong similitude between what we can observe in combustion and also in the atmosphere. We've been interested in looking at the effect of blending fuels, conventional fuels, with biofuels, a range of biofuels. And we did that using several experimental devices. The first one was a piston engine. So we burned the fuel in the piston engine, and we collected sample from the exhaust. And for that, we used the dinitrophenylhydrazine cartridges. This molecule can interact with carbonyl group, release water, and then you get a complex which can be analyzed easily by HPLC and detection by UV, because this phenyl group is strongly absorbing in the UV. And typically people do that at 360 nanometers. So I will show you some results. So these are the conditions. It was diesel engine with 4 cylinders, typical common rail injectors, and number of injectors, 4 injectors, and 3 injection per cycle. No post-treatment. So we introduce 10% of additive to a conventional diesel fuel. And we use ethanol, 1-butanol, a carbonate. I forgot which one it was. Diethyl carbonate, I believe. And we use also methyl octanoate, methyl esters, and this is a 3-propylene glycol methyl esters, and a synthetic paraffinic kerosene. And these are the results. So we plot here the total emission of carbonyl species for different fuels. This is the diesel fuel. This is the mixture with methyl esters. And the mixture with synthetic paraffinic fuel, mixture with ethanol, with butanol, with this diethyl carbonate, and methyl octanoate, and the polyether. So what we can see is that when we blend the fuel with ethanol, we increase from the reference fuel here, we increase very much the emission of a carbonyl group. Same thing with butanol, same thing with the carbonate, with the methyl octanoate, and the polyether. So the global emission of carbonyl compounds in the internal combustion engine exhaust is increasing a lot by the introduction of these oxygenated fuels. And now, if we look more details, what's going on there, we can see that in the samples, there are species which increase very much. This is the case for acetaldehyde, and acetaldehyde increases a lot when you introduce ethanol, and also acetol, same. With butanol, you have also an increase here, but you have mostly an increase with butyraldehyde. So there is a strong correlation between the structure of this additive and the species that are formed here. Acetaldehyde is very close to ethanol. When you burn ethanol, you get acetaldehyde as a main intermediate. After H atom abstraction on the alcohol, you will get acetaldehyde readily. So it will be the same in the case of butanol and butyraldehyde. They are very much connected one to the other. We also looked at the effect of these additives on the formation of soot. So this is a busy graph that was presented by Hope Mikkelsen at the 36 symposium. So it's more advanced compared to the Bocorn schematic that I showed you the first day, but it still starts from small species and radicals, which will recombine and start to form these precursors here, like small aromatics, styrene or benzene, and then you start to form polyaromatics, and then you will get large or heavy polyaromatics like coronene here, and there will be a mechanism of polymerization that will occur in this region. You start to have particle inception, and then the diameter of this structure is around 1 to 2 nanometers. And then above, you have the formation of particles, and they are growing by surface reaction and coagulation. There will be a mechanism also of carbonization, which means that your material, the concentration of carbon in your material gets higher. You can have agglomeration of these particles here and get larger structures. But beside that, you can have also an oxidation. So it's the result. What gets out of the flame here is the results of both the formation of these particulates, but also their oxidation. So it's a complicated business, and so if we go back to chemistry, these are the reactions which were proposed by Michael Franklatz and Hai Huang. This is the Hcn mechanism: hydrogen abstraction, carbon addition. So we have here the first aromatic radical on which acetylene can add, and you get this phenylacetylene. You can abstract an H atom from the ring here, and then it's possible to add again acetylene, and you get this double ring structure. And you continue this way, and finally you get something which is big. So this is the idea of this mechanism. We've been looking not in a flame, but in a jet stirred reactor, the formation of the first ring, and to do so, because here it's based on acetylene addition, so we considered acetylene. But we know that C3 species can also be important in the formation of benzene. So we selected 3 different C3 hydrocarbons: propylene, which is an olefin; propyne, or methylacetylene, which is similar to this one; and allene, which is the isomer of propine. It has two double bonds, diene, and we selected another diene with 4 carbon atoms, butadiene. So we operated in a jet reactor over this temperature range at atmospheric pressure. And we collected samples, analyzed them, and we performed kinetic modeling. And then we figure out which were, according to our model, which were the important reaction pathways. And what's interesting is that these reaction pathways are not the same when you change the structure of the fuel. Benzene formation from acetylene, but also alene and propine under our conditions mostly proceeds through C3 channel, which involves the recombination of propargyl radical C3H3 plus C3H3, which gives several C6 different intermediates, which in turn will produce benzene. In the case of 1,3-butadiene, the formation of benzene was driven by 2 competitive routes, a C2 plus C4 route and a C3 route. The first one is the fuel itself reacting with vinyl radical to produce C6 intermediates that in turn will produce benzene. And the second route is the reaction of butadiene, the radical, when we have abstracted one H atom on this structure, reacting with acetylene, which form C6 intermediates, which in turn produce benzene. But according to our computation, the formation of 1,3-C4H5 results from the interaction, from the intermediate formation of cyclopentadiene. So you have the allele radical, which react with acetylene to form 1,3-pentadiene, which after H atom abstraction, you get this radical, which in turn will form 1,3-C4H5, and 1,3-C4H5 reacts with acetylene to produce benzene. For propylene, we have an early formation of benzene, which involves a C3 route, the recombination of allyl radicals formed by H atom abstraction on propylene. This route produces 1,5-hexadiene. So you have these 2 allyl radicals, which recombine form 1,5-hexadiene, which can lose 1 H atom, form C6H9, which can cyclicize, and you get this C6H9 cyclic intermediate, which then produces 1,3-cyclohexadiene, which itself produces another radical C6H7, and finally, after losing 1 H atom, you get benzene. So you see that it's not so trivial when you change the structure of a fuel. You can get different answers. Therefore, it's very important to include all these channels, because in a complex, during the combustion or oxidation of the complex fuels, of course, you will have a large variety of species, and they will react differently or through different channels. that ultimately can produce the first aromatic ring responsible for the formation of soot as shown schematically on this slide. We also looked at the formation of soot using a laboratory flame. So we used liquid fuel. Here we use a Jet A1 and the same biofuels as before. So we pump the liquid fuel with an HPLC pump. By means of a flow of nitrogen, we atomize and vaporize this fuel. And then we mix it with a mix of O2 and N2. And this goes to the burner, similar to a McKenna burner. And we collect soot on the rod here under controlled conditions. Then we remove this rod, collect the soot that was deposited on top of it. We weight it, and we analyze the content of what's stuck on the surface. So we use these three additives that we considered before: diethyl carbonate, normal butane, methyl octanoate, and 2,5-dimethylfuran. And we operated at an equivalence ratio above 2.2. And in this time we had 20% of additive in volume. So we could extract the different polyaromatic hydrocarbons which are stuck on the surface of soot, so separate them using liquid chromatography, and analyze them by UV absorption. So these are the different species that you were interested in. These are the EPA pH that were measured. We used calibration standards in order to figure out where they were and how they responded in the UV. And what we could get is this plot. So the reference fuel is here. It gives about 3,500 nanograms of pH per milligram of soot. These mixtures give much less pH, and the mixture containing DMF forms more than 2 times pH than the reference fuel. So one comment here. These three fuels, and also this one contain oxygen. This is an aromatic ether. This one is a carbonate. This one is an ester, methyl ester, and this one is an alcohol. So you can see that according to the different functional group in the fuel, you get very different answers. And here, DMF is responsible for this very large formation of pH, mostly because you start with an aromatic ring. So even if there is an oxygen atom in the ring, the aromatic character is responsible for that. And we looked at the different classes of PAH. So we used 3 different classes: small PAH, mid-sized PAH, and large PAH. And we can see that the distribution is also changing with the fuel. The size of this disk here represent the quantity of pH that we could collect. So this one is the biggest one, and SPK is the lowest. But interestingly, the fraction of heavy pH is larger with this fuel than with the others. Of course, the composition of these fuels is so complex that it's difficult to propose any good reason for these results. And, but it clearly indicates that it's not because you are using a bio-derived fuel like this one that it will be a cleaner fuel. It's not always the case. I have one question I will answer. According to slides 214, soot and pH, is it possible, for example, to estimate the CO2 concentration of other species around the propagation axis of the burner? Okay, let's go to slide 214, but I think I cannot. Okay. I simply don't understand the question. So I cannot answer you. Sorry for that. I propose we stop now and we get back. So it will be 1 p.m. I guess. All right, so let's go back to this business of formation of pH and analysis on the surface of soot. So I draw the structure of the different additives. So this is DMF, this is DAT carbonate, butanol, and methyl octanoate. And when we summarize the result, what we can see is that again, this is with this fuel mixture that we have the largest formation of PAH, followed by this one, the reference, and then the 3 others which are less. We have a detailed speciation of the different polyaromatic hydrocarbons collected on the surface of soot. And then using this equivalent toxicity, which was developed by Nisbet and Legoy, we could draw some tendency. We can see that potentially the toxicity of soot particulates just based on pH collected on their surface is decreasing when we use SPK or methyl octanoate or diethyl carbonate or butanol, compared to regular soot samples for the reference fuel, but dramatically increases in the case of 2,5-DMF. We looked also at another type of interaction between NOx and HC, which is somehow closely related to what's going on in the atmosphere, where if you remember what I presented earlier here. So there is an interaction between NO and the radicals formed by oxidation of unburned hydrocarbon present in the atmosphere, and also interaction between HO2 and NO. And so in combustion, it can be the same, and it's a different. So it's different from reburning. And this was initially called mutual sensitization, which means that when you introduce NO in a mixture of, for example, methane and oxygen diluted by nitrogen, the interaction will favor the oxidation of NO into NO2 and favor the oxidation of methane. And this goes through interaction between NO and HO2 and CH3O2 in the case of methane. So we did experiments at 1 and 10 atmospheres, and we studied the conversion of NO to NO2 by CH3O2. And we observed that it's more important below about 800 Kelvin than at higher temperatures, where the reaction of NO with HO2 dominates the production of NO2. And the NO to NO2 conversion is enhanced by the production of HO2 and CH3O2 radicals from the oxidation of the fuel. So the production of OH resulting from the oxidation of NO by HO2, NO plus HO2 giving NO2 plus OH promotes the oxidation of the fuel. So NO plus HO2 giving NO2 plus OH is followed by OH plus methane giving CH3 plus water. So at low temperature, the reaction further proceeds via peroxidation of methyl radicals to form methyl peroxide. And methyl peroxide reacts with NO to produce methoxy radical and NO2. And at higher temperature, production of CH3O involves NO2 through the reaction CH3 plus NO2 giving CH3O plus NO. So the sequence of reaction CH3O giving CH2O plus H, CH2O plus OH giving HCO, and HCO plus O2 giving HO2, and H plus O2 giving HO2. CH2O plus H or OH give HCO, and HCO plus O2 give HO2, and H plus O2 give HO2. And these HO2 transform NO into NO2 and produce OH radical. So this is what's going on. And now I will show you typical results that we could observe. So first of all, this is the consumption of NO, and in parallel you get the formation of NO2U. And on this plot, we show the oxidation of methane to produce intermediately CO, but also CO2 and water. And intermediate formation of ethylene here, and that of formaldehyde. So these are the experimental results obtained when we have under fuel lean condition. When we have only I'm sorry, I think I did something wrong. When we have for the open symbols, we have no NO added, and we get this regarding the consumption of the fuel. And when we put NO, we start to oxidize at much lower temperature, and it's a progressive conversion, whereas here it's a dramatic oxidation that occurs over 20 degrees about. But you see the big difference, the big gap between the two profiles, which are due to the presence of NO. And yeah, I was looking for the concentration of NO. So we introduce here 200 ppm of NO. So this sensitization is strong when you introduce small quantities of NO. If you were using very high concentration of NO, then the behavior would be different because there would be some additional reaction playing a role and diminishing the impact of NO on the oxidation of the fuel. So these are other examples with the different mechanism, because before we were considering several mechanisms from the literature. All right, so you can see here the strong effect, and this is at 1 atmosphere. And now if we continue and we do the same at higher pressure, still methane and NO, still fuel lean, and we have I think that we have also 200 ppm of NO added or not added. So here, this is the baseline, let's say. We don't put NO in the system, and we see the oxidation of the fuel, formation of formaldehyde as an intermediate. And once you introduce 200 ppm of NO, there is an even bigger effect since the reaction starts just above 800 Kelvin, whereas here you have to wait until 1060 K to get some reaction. So huge effect, even bigger when you increase pressure. And similarly, the conversion of NO into NO2 is also stronger than what we could observe here at atmospheric pressure. We did some additional experiments. So far we were in fuel lean conditions. These are performed the stoichiometric conditions. We still use 200 ppm of NO, and we can see here the consumption of the fuel, formation of the products, water, and CO2 here. and the intermediate formation of CO, and conversion of NO into NO2, and the formation of formaldehyde. The model doesn't represent very well the data, but the trends are there. And this is another example under different conditions. Here we were under stoichiometric conditions. Here we are in few lean conditions. And under few lean conditions, here we are at about 70 ppm of formaldehyde. Here we are slightly above. And well, the model fits well the fuel profile, but there are some discrepancies for some of the intermediates and for NO, and whereas NO2 is not too bad. Here we operate. These are literature experiments performed in a flow tube, flow reactor at atmospheric pressure. So we simulated their experiments, and we see the consumption of NO and the formation of NO2. And they plotted the NO2 over total NOx as a function of time, and in two different conditions. And so this time they used, the experiments from the Japanese group of Professor Ori, and they used a much smaller quantity of NO in these experiments. This is a comparison. So at 10 atmospheres of different models taken from the literature on the to simulate these mutual sensitization experiments performed with methane, and you can see that from one kinetic model to another, the answer can be quite different. We looked at the different pathways which are responsible for the consumption of NO. And so again, what we can say is that here, this reaction is extremely important. It's that of NO with HO2. It's followed by that of CH3O2 with NO. So we have here the pathways both at 1 atmosphere, which are the continuous line, so those. And dotted lines are for the 10 atmosphere conditions. And you can see that the same reactions play a role, play the same role, but it's clear that when you are at 10 atmospheres, these reactions are, this reaction is much more important than at 1 atmosphere. If we try to schematically represent what's going on, so we have here the fuel chemistry, and here we have reactions which are due to the presence of NO. Methane is oxidized by OH radicals to produce CH3. CH3 can react with O2 to produce CH3O2, which by reaction with O2 will produce formaldehyde, which will also oxidize and produce HCO. HCO can decompose or react with O2 to produce CO, and CO is oxidized by OH to produce CO2. And now the interaction between Nox chemistry and the hydrocarbon chemistry comes from several reactions. The reaction with HO2, which converts NO into NO2 and produces OH radicals, which will help oxidizing methane. Also, the reaction of NO with CH3O2, which is formed by addition of O2 to the methyl group here, to the methyl radical, it will produce CH3O. And CH3O can react with NO to reform CH3 and produce NO2. What else should I let's see? I think that's about it. Modelers figure out that the prediction of the formation of methyl peroxy radicals is very sensitive to the ether formation of CH3O2. And if you vary over a range from 2.5 kcal per mole to 6.1 kcal per mole, you can see that you vary by almost a factor of 4 the maximum concentration of CH3O2. But even though it has not major impact on the predicted concentration profiles of NO or NO2, because this is not the major route. The major route is through HO2. So I would like to go back to this, because when I'm teaching this interaction between NO and hydrocarbons here, students sometimes get confused. And we must differentiate between two different regimes. Of course, there is not a clear frontier between these two, but there is one regime where we are dealing mostly with oxidation, and one regime where we are mostly dealing with NO reduction. So in this regime here, NO is transformed into NO2 through these two reactions, mostly. Whereas at higher temperature, this is less and less important, and the main routes are those written here. The reaction of NO with HCCO, forming HCNO, HCNO being reduced by reaction with H atoms, producing HCN, and the other reaction of NO plus HCCO giving directly HCN. And then there is this channel that we described previously, HCN being oxidized in HNCO, which can be reduced into NH2 and itself forming NH. And both NH and NH2 react with NO to form N2. and two other products, either OH or H2. So when you operate over a wide range of conditions, so you can observe both the mutual sensitization of the oxidation of NO and of the fuel, and then transition to reduction with the appearance of HCN. Once you observe HCN, you are under reduction, NO reduction conditions. And when there is no HCN produced, you are under mutual sensitization, oxidation, and oxidation regime. Another oxidant that can interact very effectively with hydrocarbon is ozone. So when I showed the table representing the different unburned hydrocarbons which are present in the troposphere, I told you that unsaturated species will react with ozone and form an ozonide. So you will have, so at the beginning you have, at the beginning you have a double bond. And on this double bond, you will add ozone. And then you will get this ozonide, which will decompose and form oxygenated species. But when you have a normal alkane or branched alkane, this reaction cannot occur. So here we did some experiments using a piston engine where we burned an hydrocarbon and sent, produced ozone in an ozonizer. And this goes together with air to the plenum, and then we introduce these in the engine. And what we could see is that the addition of ozone has a strong effect on ignition. So here we plot the heat release rate as a function of crank angle. And you see here there is a tiny heat release corresponding to cool flame. And then you have the main flame occurring here. And if we zoom this zone here, what we can see is that when there is no ozone added, there is almost no heat release. Whereas when you start to put only 10 ppm of ozone, you start to see heat release here, and even bigger with 40 ppm. So what's going on? Well, without ozone, you have the fuel that has only oxygen to react with. It's a slow reaction, as I said before. It can produce HO2 plus a radical from the fuel. And this reaction is followed by the reaction of HO2 with the fuel, which is not a very fast reaction. And you get H2O2. So overall, until this reaction, it's a relatively slow process. Once you introduce ozone, ozone readily decomposes into O2 plus O, and O reacts with the fuel, abstract an H atom, forms OH, plus a radical from the fuel. And this reaction is followed by the oxidation of the fuel by OH. You have H abstraction from the fuel, forming H2O plus a radical from the fuel. And this process is fast. So if you looked at the effect on in-cylinder pressure as a function of crank angle with different initial concentration of ozone, and again, these are very, very small concentrations. So we have no ozone added here, and then we start to put 1.3 ppm, and we get nice ignition with 2.8, 5 ppm, 8.5 ppm. And if we plot heat release rate as a function of crank angle, again, well, you see two effects. You get earlier ignition and more efficient ignition. We did similar experiments with other oxidizers. We compared the effect of ozone, of NO, and of NO2 on the ignition of a fuel in an engine. So the reference case is here without any additive. Then if we introduce nearly 20 ppm of N2O, we get this in-cylinder pressure. With the same amount of NO, we get this one. And with the same amount of ozone, we get this profile. So you can see that we have increasing effect from NO2 to NO to O3. And this is the same story regarding heat release rate. So we have a stronger effect on heat release rate, starting from no additives, with moving to NO2 to NO and O3. And also you have an advance of ignition, which occurs. So if we look at the difference between crank angle 50 and crank angle 50 without any additive, as a function of concentration of the additive. For ozone, we have this curve. With NO, we get this one. With NO2, we get this one. So again, minor effect by the addition of NO2, bigger effect with the addition of NO, and huge effect when you add ozone. So how to interpret these results? You can interpret them by running a chemical kinetic reaction mechanism. This is what we did. We did very simple computations, zero-dimensional. When we add ozone, ozone mainly decomposes into oxygen atoms and O2. This is a very fast process. After being formed, O atoms attack the fuel and produce OH radicals, which will rapidly oxidize the fuel. So we have isoctane plus oxygen atoms, giving this octyl radical plus OH. And then this OH attack also isooctane to produce water and another fuel radical. And overall, this reaction is fast. When you use NO as an additive, NO is mostly consumed by reaction with HO2, which are produced by the reaction of the fuel with O2. And again, it's a slow process. HO2 can be produced by reaction of these HO2 radicals with NO, and it's a fast process. Therefore, rapid fuel consumption can take place via this route here due to OH production. Sorry, through this route here due to OH production via the interaction of NO with HO2. Thus, as nitric oxide requires an HO2 radical to yield an OH radical, this explains the lower effect of NO on ignition delays compared to ozone. And finally, nitrogen dioxide addition. So OH production results from the reaction of CH3 plus NO2, giving CH3O plus NO, and NO2 plus HO2 gives HONO plus O2. HONO can decompose and reform NO and produce OH. And NO can also react with HO2 to produce OH. As nitrogen dioxide presents intermediate reactions before it can yield to the formation, it can lead to the formation of OH radical. Its effect on ignition delays is the lowest of the three additives. So this one, very fast because you produce readily an atom which attacks the fuel and produce another very reactive species which attacks the fuel also. Here, the initial formation of H2O is slow. This is the bottleneck of the process, because once it's produced, there is these fast reactions that it is producing OH, and then you are able to oxidize the fuel. And here, well, it's more complicated to produce OH radicals. Therefore, the whole process is slow. We looked at the effect of ozone and NOx on the ignition of a variety of fuels. On methanol, so we can see the effect here. So in terms of in-cylinder pressure, which is increasing with increasing addition of, so you can see here it's addition of ozone. And same thing with ethanol, and same thing with butanol. So every time you increase the initial concentration of ozone, you get a larger effect. So I will summarize what I said. So we've seen that the formation of NOx can occur through different mechanisms. The first one we presented is the Zeldovich mechanism, or high temperature Nox formation, thermal NO. This is the attack of N2 by O atoms, and then production of nitrogen atoms that can also interact with oxygen or OH. This has a very high activation energy. That's the reason why it's only occurring under conditions where the temperature is high, typically in the front flame. Prompt NO is different. It's the attack of molecular nitrogen by radicals coming from the fuel, like CH2, CH, or even C. This process can occur at a lower temperature. The third mechanism that was presented is that of N2O. So it's favored by high pressure because N2O is formed by N2 plus O2 plus a collider. So increasing the pressure will increase this rate of reaction and favor the formation of N2O, which then will react and with different species and can produce N2. The Nnh mechanism is also possible, but usually this mechanism is of less importance compared to these three others. And finally, I presented the fuel mechanism. In this case, nitrogen is coming from the fuel. It's let's call it organic nitrogen. It's a nitrogen atom that can be present in aromatic structures or saturated structures or amine functions. And its oxidation will go either to the intermediate formation of HCN or the intermediate formation of ammonia. But both by oxidation will produce NO. We've presented the reduction of NO by two different processes. The first one is the selective non-catalytic reduction of NO, where we use ammonia, which interacts with NO through the formation of NH2 and NH, that by reaction with NO form molecular nitrogen. However, there is a undesired formation of N2O in this process. And also, there is a small temperature window around 1250 K where this process is working well. Below this small temperature window, it doesn't work well. And above, you get lots of N2O. We've seen that if there is a presence of SO2, then SO2 will not really limit the conversion of NO, but it will move the optimum to higher temperature. Then we looked at NO reburning by fuels. So I gave you an example with methane, but with methane or natural gas, but there are other fuels which can be used. And in the lab, we performed many experiments with different hydrocarbons, and we showed that the key process is that involving HCCO. And also I demonstrated you based on the experimental observations that HCCO is very quickly produced by oxidation of acetylene. And acetylene can be intermediately produced during the oxidation of ethylene, and itself ethylene can be produced by the oxidation of propylene, but also of saturated hydrocarbon, because it's a ubiquitous intermediate during the oxidation of most of the hydrocarbons. So reburning is a process where you have several stages. In the first stage, you are producing NO under close to stoichiometric conditions, and then you are creating a slightly rich zone. You don't need to go very far in equivalence ratio. Something around 1.2 is enough to, or even below, to have a reducing condition. But during this process, you are forming undesired species like HCN that you don't want to send to the troposphere, to the atmosphere. Then you have a third stage where you introduce additional air to burn these intermediates, which have not been transformed into molecular nitrogen. Then we presented the reactivity of unburned hydrocarbon and some processes that can produce soot. And finally, also beside that, we looked at the different components that can be present on the surface of soot. And we could see that when we are blending conventional fuels with biofuels, there can be some positive or negative effects. So in terms of pH, most of them are probably interesting in terms of pH reduction. But one of them, we saw that dimethyl THF is not good. It will produce more soot and more pH than conventional fuels, even when it's a dropping fuel at a very small concentration. We also presented the effect of these additives on the formation or emissions of carbonyl, aldehydes, and ketones. And again, you could see that when you are using especially alcohols, then you increase significantly the amount of aldehydes in the exhaust. And this can be a problem because nowadays we are using fuels which contains increasing quantities of ethanol. We looked at the effect of trace species on ignition, Nox. I will finish with that, and ozone mostly. We could see that ozone has the capability to start ignition very quickly because it will readily decompose and produce an oxygen atom, which by reaction with the fuel will produce an OH radical, which itself will attack the fuel and oxidize it further. And this can be efficient at free trace level, like a few ppm. And then to finish, the interaction between NOx and hydrocarbon. Once more, I want to emphasize that depending on the temperature, there are different processes which occur. In the first regime here below about 1100 Kelvin, we have an oxidation process that occurs. NO is oxidized into NO2 by reaction with HO2 or RO2, which produce active species which can interact with the fuel. So OH will interact directly with the fuel and increase its oxidation rate. And these alkoxy radicals here can produce HO2, which will feed the first reaction and in turn increase also the production of OH and the oxidation rate of the fuel. So this is occurring in this regime. At higher temperature, it's a different story, and we are back to NO reburning with formation of HCN. And to figure out what are the major processes you are dealing with, you can look at the formation of NO2 and HCN. If you see HCN produced, it means that you are in this regime of NO reduction. And if it's mostly NO2, then you are in the mutual sensitization regime that occurs here. And again, this set of reaction is very similar to what's going on in the atmosphere, where you have production of ozone through the photolysis by sunlight of NO2. And I think this is it for today. I don't see questions. If you have questions before we quit, I am ready to answer them. No questions? Either I was very clear or you are exhausted. Okay, so how to operate an ozonizer? Well, you feed it with oxygen, and so in this device there is either a discharge or a UV lamp, which will break oxygen-oxygen bonds, and then the O atoms will recombine with molecule oxygen and produce ozone. So it's no black magic. There are ozonizers that can be that are commercially available. Anything else?